In this video, we're going to talk about the concept of the limit of a function. So suppose we have a function f of x that approaches some value L as x gets sufficiently close to a point A. Then we say that the limit as x approaches A of f of x is equal to L. Now graphically, what this is saying is we have something like the following picture. And so we have this function f of x, and we've got this point A. And now notice that as we get closer and closer to the point A on this graph, so if I take some interval around that point A, I'm getting really close in value to this point L over here on the y-axis. And so this is the idea of the limit, is that as we zero in on this point A, pushing towards the point A from both sides, the y value of the function is zeroing on this value of x, of L. And so this is the idea behind the limit of a function. And limits make up pretty much the basis of all of what we do in calculus. And so this idea is very useful to consider. So let's look at an example with an actual function. So suppose we have the function f of x equals x minus 1 over x squared minus 1. So if we have this function, if we look at points on this function, if we plug in 0.5, the output is 0.66. If we plug in 0.9, the output is 0.526. And if we were to plug in 0.99, the output is 0.502. So now notice, as we get closer and closer to the number 1 from the left, these values seem to be approaching the value of 1/2. And the same thing happens if we look at from the right. So if we take 1.5 and plug it in, we get 0.4. If we plug in 1.1, we get 0.476. If we plug in 1.01, we get 0.4975. And so once again, we see that as now we're approaching from values above 1, but are still going towards 1, our value of the function is approaching this value of 0.5. And so we would say that the limit as x approaches 1 of x minus 1 over x squared minus 1 is equal to 0.5. And so this is how we look at it from a table point of view, is we just pick values that are getting closer and closer to this point that we care about, which in this case is the x value of 1, and we see what are the y values doing. And here we say they go towards 1/2. So now another example that we could look at is if we take the limit as t goes to 0 of the square root of t squared plus 9 minus 3 over t squared. Once again, we're going to plug in values, but this time we're going to plug in both the left and the right at the same time. And so the benefit of why we can do that in this case is notice that we're squaring the t in both places it shows up. And so t is squared in both places where it shows up. And so if I plug in a value of t less than 0, it gets squared to be positive. And so the negative and positive of the t value will have the same output. And so because we're approaching 0 in our limit, we can kind of approach both sides at the same time. So if we plug in plus or minus 1, we get 0.162277. If we plug in 0.0, not 0.01, 0.1. We get 0.1666620. If we plug in plus or minus 0.05, we get out 0.166655. And so it looks like we're approaching this value of 0.166 repeating, and this actually is the value of 1/6. And in the next video, we will talk about how to compute limits rather than just from a table, but actually from the formula, and we will see that we actually do get 1/6 in this limit. Now, an important idea with regards to limits is that we only care about what happens near the point A. We don't actually care about what's happening exactly at the point A. And so if we look at the graph of the following function, where we have a hole at the point A, now notice that as I approach A from the left, I'm going towards where that hole is, and as if I approach from the right, I also go towards where that hole is. And so where this hole is a value L. There's just some y value corresponding to that hole. But since the function is approaching that point, even though the function is not defined at that point, we'd say the limit as x approaches A of this function, which I will call f of x, the limit of this function is equal to L still as x approaches A. So even though the function isn't defined at that point A, the limit still will go towards L because that's what the points are approaching. And the same is true even if I was to define some other point down here. So if we will say f of A was this value down here, that doesn't actually change the limit because the limit doesn't care what the function is at the point A, just what we're approaching as we go towards A. And so having holes has no real impact on the graph, on the limit. It impacts the graph, but not the limit. So now, limits do not always exist. And so there are several ways the limit might fail to exist. The first and the most common that you might see is that the limits just aren't going towards the same thing if you approach from different directions. So if we look at the function h of x equals 1 if x is less than 0, and 2 if x is greater than or equal to 0, then we have the following graph. So when we're less than 0, we're at 1, and when we're greater than 0, we are at 2. And so now, if I was to take the limit as x approaches 0 of this function h of x, we see when I'm approaching from the left, my values are going towards 1. That's not hard to see because all the values are 1, and so no matter how close I get to 0 from the left, I'd be approaching 1. And if I approach from the right, then I'm going towards 2. And these are not the same number. So if I approach from different directions, I get different answers. And so in this case, this limit does not exist. And in mathematics, we get kind of tired of writing does not exist every time, and so we typically denote this as DNE, just to say the limit does not exist in that case. This limit does exist if we only look from one direction rather than both directions. And so we want a concept for this idea of just approaching from one direction. And in mathematics, we usually are not very creative in naming things, so we're going to call these exactly what I have been calling them. So if the function f of x approaches the value L for all values of x less than A as x goes towards A. From below, we say the left-hand limit exists and equals L. And then we'd write the limit as x approaches a from the left of f of x equals L. And so this superscript of a negative sign just says we're going from values below the point A. And so in our graph above, for this function h of x, the limit as x approaches 0 from the left of h of x equals 1. Because we saw as we go towards from just the left, we're going towards this value of 1. And now there is nothing special about going from the left, and so we can define in much the same way the idea of going towards it from the right. And so if the function f of x approaches the value L for all values of x greater than a as x goes towards a from above, we say the right-hand limit exists. And equals L. And we denote this as the limit as x approaches a from the right of f of x equals L. And so we write a plus superscript if we're approaching from the right. That's just saying we're taking values above the point A and approaching from that direction. And so in our graph above, if we are approaching just from the right, we only care about values above. And we said there that the limit in this case for h of x was equal to 2. And so both of the one-sided limits, these are called one-sided limits because we only approach from one side, both of the one-sided limits for this function h of x do exist. However, the overall limit does not exist, and the rationale for that is that we have the following. The limit as x approaches a of this function f of x equals L if and only if the limit as x approaches a from the left of f of x equals L, and the limit as x approaches a from the right of f of x equals L. So we need both the left-hand limit and the right-hand limit to go to the same point for our limit to exist. And so this is primarily where functions fail to have a limit at a point, is because the left-hand limit and right-hand limit do not agree. Now there are other ways that we're going to talk about of why a limit might fail to exist. This is one of the more common ones to see. So now we're going to look at an example of actually computing limits from a graph using this idea of left-hand and right-hand limits. So we have the following graph. And so this is going to be our function y equals g of x. And we want to talk about in this graph a few limits. And so first, notice if we take the limit as x approaches 2 from the left of g of x, then that means we only care about these values when we're below 2 and going towards 2 from the left. And so in this case, we're approaching the value of 3. and the limit as x approaches 2 from the right of g of x. Now we only care about values above 2, so we're approaching from the right only, and that goes towards 1. And so we see that this function will not have a limit at 2 because the left-hand limits and the right-hand limits do not agree. But if instead of looking at 2, we looked at 4, now notice as we approach 4 from the left, we're going towards 2, and as we approach 4 from the right, we also go towards 2. And so in this case, these are equal to each other. They are both 2. And so the limit as x approaches 4 of g of x would be 2. And now this is the case even though in this example we have that the function at 4 is not defined to be the value of 2. It's defined to be the value of 1. We have that g of 4 is equal to 1 from the graph. But that doesn't matter, because as we mentioned before, the limit only cares about what happens when we get close to the point, not when we're actually at the point. So the next way that functions might fail to have a limit is what we call a wild oscillation. And so this one is a bit hard to actually picture, but the idea is that basically we can approach multiple values as we get closer and closer to something. So we're going to look at the following function. F of x equals sine of pi over x. So now notice, if I look at f of 1, this equals 0. If I look at f of 1/3, this would be sine of 3 pi. I'm just flipping the 1/3. And sine of 3 pi is also 0. And if I look at f of 1 over 1,000, so I'm getting really close to 0 now, this would be sine of 1,000 pi. And that is still 0. So it looks like as I approach from the right, I am going towards the value of 0. Now there's nothing special about taking the positives here. And so f of negative 1 is also 0. F of negative 1/3 is also 0, and f of negative 1 over 1,000 is also 0. So it looks like this limit might be going towards 0, namely the limit as x approaches 0 of sine of pi over x. It looks like it may be going towards 0. But what if we were just to pick things a bit differently? So instead of picking the values we were, what if we picked f of 2/5? Well, this would be sine of 5 pi over 2. Sine of 5 pi over 2 is 1. And then we could also look at f of 101 pi, not 101, 2 over 100 and 1. So if we looked at this, this would be sine of 101 pi over 2, which is also 1. And if we looked at, say, f of 2 over 1,000 and 10,001, this also can be shown to be 1. And then you can take the negatives. You can't take the exact negatives because sine doesn't work quite the same way as you approach 1. But the values here are all going towards 1. And so the way we picked our points actually mattered here. And so if we picked them in one sequence, we were getting zeros. If we picked them in another, we were getting 1s. And so what's happening here then is that this limit actually will not exist. And so the limit, as x approaches 0, of sine of pi over x does not exist. And it's because it's not really going to just one value. Now graphically, what's happening here is the function does something like the following. And admittedly, I am not going to be able to draw this really well, but what it does is it takes on waves that are going between 1 and negative 1, and these waves get increasingly close. They become increasingly rapid, and so they change faster and faster as we approach the value of 0. And the same thing is true if you approach from the left. And so these waves, which I can't essentially draw them, but they get increasingly close to each other. And so we have wild oscillations, basically meaning that it will change rapidly between the values of 1 and -1. And now we hit every value between 1 and -1. And so when we zero in on the point, it basically looks like this crazy mess that I'm drawing here, that you can't even tell the difference between any one point. You just get kind of like a black box. And if you were to graph this on some application like Desmos, you'd see that this is what happens. And so this is another way that limits can fail to exist. Now there's a third way that a limit might fail to exist. And we're going to look at another example to see what happens in this case, as this case is a bit more useful even though the limit does still fail to exist. So we're going to look at the limit as x approaches 0 of 1 over x squared. And so in this case, we have our function. We're going to create a table like before. And now, once again, I'm squaring everything and approaching 0, so the plus and minus are going to have the same output. So if I plug in 1, I get out 1. If I plug in plus or minus 1/2, I get out 4. If I plug in plus or minus 1 over 10, I get out 100. If I plug in plus or minus 0.001, I get out, I think it's 100,000. Yeah, you get out a million, sorry. And so notice I'm getting really large values. As I get closer and closer to 0, I'm getting larger and larger values. And so in this case, we still say the limit does not exist. So the limit does not exist in this case. But we do know something that it's doing. Namely, it's getting really large. And so even though the limit doesn't exist, it's not going towards just some number, we do know the behavior of it. It's going towards something, namely, it's getting exceedingly large. And so what we say in this case is the limit as x goes to 0 of 1 over x squared equals infinity. Now this equals is a little bit of a vague equals, as the number, infinity is not a number, so you can't actually be equal to it. But this is basically just denoting we're getting large without bound. And this is a useful information to have, as unlike the wild oscillations, or just the left hand and right hand limits not agreeing, we do know what's happening here. We're getting larger and larger, which does tell us something about the function. Now graphically, what's happening here is the following. And so we have, this is actually the graph of the function we're just looking at. This is f of x equals 1 over x squared. And so notice as we approach 0, we are going off to infinity. We're getting really, really large. In college algebra, you might have talked about this idea of having a vertical asymptote. And that's exactly the idea that we have here, is this idea of a vertical asymptote. We have some vertical line we're getting really, really close to, but never actually touching. And now we can do this towards negative infinity just as easily as positive infinity. And so we could have something like the following. So we have some point A here, and the function could get really close to negative infinity. So it could be getting negative without bound, in which case we'd say the limit as x approaches a of this function f of x equals negative infinity. And now these are both equally viable limits to have, but once again, we aren't really getting a value out. We're getting out this idea of infinity or negative infinity, which is just telling us this idea that we have a vertical asymptote, or that we're getting really large, either positive or negative. And so I keep saying this term of vertical asymptote, so let's actually define what that means. And so we say the vertical line x equals a is a vertical asymptote of the curve y equals f of x if at least one of the following is true. So we could have the limit as x approaches a of f of x equals infinity. The limit as x approaches a of f of x could be negative infinity. Limit as x approaches a from the right of f of x could be infinity. Or the limit as x approaches a from the right of f of x could be negative infinity. The limit as x approaches a from the left of f of x could be infinity, or the limit as x approaches a from the left of f of x could be negative infinity. And so if any of these 6 limits holds true, we say that we have a vertical asymptote. And so we don't care if the two-sided limit actually does it. We only care if at least one of the one-sided limits goes towards positive or negative infinity. And so graphically, we have things like the following happening. And so we could have some point A where the function is doing any number of things, but it's approaching from the left infinity. And so here we'd have the limit as x approaches a from the left of f of x equals infinity. And now it could be doing who knows what from the right. So maybe the function does something totally normal on the right and it's not shooting off to infinity. We'd still have a vertical asymptote at the point x equals a. And the same idea holds true if you approach from the right. And so if we approach from the right, say we have this point A, we could have a vertical asymptote here, even though the function might be doing any number of things from the other direction. And it could even be defined at the point A as long as it's a piecewise function. And so because of this, we'd have still in this case that the limit as x approaches a from the right, in this case, would be negative infinity. And so this is the idea of a vertical asymptote, that as long as one of the one-sided limits goes towards positive or negative infinity, meaning that it's growing without bound either in the positive direction or the negative direction, then we have a vertical asymptote. And so let's look at one example of checking for a vertical asymptote. So we're going to have the function f of x equals x over x plus 3. Now, one thing to be aware of is vertical asymptotes can only happen at points that aren't in the domain of the function. And so this function has a domain of everything other than minus 3. And so the reason why we know that is true is because we can't divide by 0, and if we plugged in negative 3, we'd be dividing by 0. But other than that, this is a rational function, so its domain is everything other than that point where we'd be dividing by 0. So if we have vertical asymptote, it would happen at negative 3. And so let's look at points as we get close to negative 3. Now remember, we don't actually need to check both sides. We only need to check that there is a side where it approaches infinity or negative infinity. And so if we plug in points towards approaching negative 3, we could plug in something like x equals negative 2.99. Well, if we plug that in, we'd have f of negative 2.99 is equal to negative 2.99 divided by 0.01, which equals negative 299. If I picked negative 2.9999, divide this by 0.0001, so this would be f of negative 2.9999. This is negative 29999, so almost negative 300,000. And so we're getting very large numbers as we go in the negative as we go towards towards negative 3 from the left. And so this idea then tells us that the limit as we approach, I said from the left, this is from the right. Notice I'm taking values that are above negative 3 on the number line. So on the number line, -3 is here, and I'm taking values that are approaching from the right. And so we have the limit as x approaches -3 from the right of this function f of x is going towards -infinity. Now you can check if you approach from the left, you're going towards positive infinity. And so this still has a vertical asymptote, the line x equals -3. It just has a vertical asymptote that does something like the following. And so if we approach -3 from the right, we're going towards -infinity. And as we approach -3 from the left, we're going towards infinity. And so I'm making up what it looks like beyond those points. But that's all that's happening in the graph, is from the left, we go towards positive infinity, and from the right, we go towards -infinity. And so we'd still have a vertical asymptote at this line of x equals -3. And so that is all for the concept of the limit. So limits are very useful in finding vertical asymptotes, as we just barely talked about. And we'll see more uses of them in future videos as we start to use this idea of the limit to develop more structure.